Hey everybody, second of 3 videos on sets informally here on the whiteboard. This time we're going to be talking about some predicates on sets, in particular membership, subset, and equality. These are the predicates that you'll be implementing in your homework, so I figured these are the best ones to cover. Okay, let's get started. We already saw some nice examples of sets in the last video, like bool, day, right, Sunday, Monday, Tuesday, Wednesday, Thursday. I don't know if people are used to this notation where R becomes Thursday because there are 2 T days, but this is pretty common. Friday, and then 2 Saturdays. What are we gonna do? What do I call it? D. I don't know. Whatever. Let's call it. So whatever. We've seen sets like this, and I want to talk about some predicates on sets like this. So let's start out. We'll begin with membership. So, an element of a set is a member of that set, i.e., it is in it. Element member set. Okay, let me see if I can change this out of my example blue. Yeah, let's make it perfect. All right, so that's what an element is. So let's look at some exemplary notation. Oops, let's turn you orange also. Great, thanks. Okay, so let's do it. So the notation is we would say X is in A. Or just X in A. So you might wonder about this notation. Right, it's commonly written one of these two ways, i.e., it's an epsilon. From the Greek word en, meaning in. Sensible enough. I saw someone say recently that Greek letters are like emoji for people who do math. And honestly, I really love that idea. It's a way of kind of expressing things in a funny way. It also means you don't run out of Latin characters, which we save for variables. So Greek is just going to make a lot of appearances here. Okay, cool. So let's look at some examples of things that are in other sets. So true is in bool. Monday is in day. 3 is in that, which is this. Oh, it's very sloppily written. Let me write that better. Which is the same thing as nat. Right? Those are a bunch of positive examples. Let's look at some negative examples. Maybe is not in bool. Is not in. So it's just a slash through the letter. Blur's day is not in day. Right? And then like 5 is not in the empty set. Now, in fact, here, I could write anything I wanted and this will be true. Nothing is in the empty set. Okay, so that's membership, or is element of. A super common predicate. People use this often to define sets, right? You can define a set by characterizing all of its members. Okay, so there's our first little bit. Let's get our definitional orange going. So that's our first operation. So this is the is in operation. Okay, next up, let's do the subset of operation. A set X is a subset of a set Y if every member of X is also a member of Y, right? And then we write it with this notation. Whoops. Right, so let's do some examples. So the set true is a subset of bool. The set false is a subset of bool. Right? So why is that? Well, true is a member of bool. So is false. That's fine. There's more stuff in bool. Here the set false is a subset of bool. Why? Well, false is in there, and false is in bool. And then everything else is gravy. Some more surprising facts. Bool is a subset of bool. Well, why is that? Well, everything is a subset of itself, right? Because if it's an element of itself, then it's an element of itself. In that sense, this is a little bit like, this resembles less than or equal to. Now there are some differences where, like, you can come up with, for less than or equal to with two numbers, either one is less than or equal to the other or vice versa. But let's look at some counterexamples. Bool is not a subset, is not a subset of day. So again, using this slash to mean is not. But then it's also the case that day is not a subset of bool. So this is something that doesn't happen for LEB less than or equal to, right? Here, it's really what's called a partial order. It might be the case that things just aren't related by the subset relation in either direction. Common enough. One or two other examples. Okay, the empty set is a subset of X. This is true for all sets X, because there's no elements in the empty set. Similar true thing we can say, if X is a subset of the empty set, then X has to be equal to the empty set, because there's no elements in the empty set. It kind of forces it. Okay, one last common useful thing that I'm just going to mention so you know about it. We're not going to talk about it much more in this file. X is a proper subset of Y if X is a subset of Y and X is not equal to Y. That is, i.e., id est, there is some element of Y that isn't in X. Okay, so let's look at some examples. A common way of writing this is this, where the slash goes just through the equal part. Right, that's the standard notation. So true is a proper subset of bool. Empty set is a proper subset of day. Even numbers, I'm not going to write down this set, but I think you know what I mean, are a proper subset of the naturals. Right, so you'll also see this notation, written just that way. And sometimes people will write this could be proper or not. So that notation I find really confusing. I really don't like using just that notation. I think it's worth avoiding, right? It's much clearer to either write it with the little line here, this subset could be equal, and subset is not equal, and then people will know exactly what you mean. Okay, let's do the last one. A set X is equal to Y if they have the same elements. And for that, we would just write X equals Y. So another way to phrase that might be something like X equals Y when X is a subset of Y and y is a subset of x. And to see why that's true, you can kind of unfold the definition of this subset could be equal operation, saying like, well, look, everything that's in x has to be in y, and everything that's in y has to be in x, so they have to have the same elements. Okay, so that's just sort of the way to define set equality, right? So notably, we might say things like this that will come across as surprising at first. The set true, false is equal to bool is equal to the set false, true. Order doesn't matter. Now, I want to be very clear because when you get to the code, you'll see that, well, wait a minute. Some of your representations of sets, Prof. Greenberg, critically depend upon order. So which is it? And let's be really clear here. For the informal idea of what constitutes a set, for what makes two sets equal, for how we think about sets generally in our own minds, order doesn't matter. Now, on a computer, to get an efficient representation or a useful or a good representation along some axis of goodness, some measure of why things would be good or bad, we might care about ordering, and that's fine. We're not saying that sets are ordered. We're saying that our representation of sets will use order to do a good job. Those are two really different ideas, and it's important that you be able to separate the general abstraction of what constitutes a set and the representations that we'll actually implement on a computer. There are lots of differences. So, for example, we might come up with a representation of sets where we'll only get one of these two, right? It'll be impossible to talk about the other. We might come up with a representation of sets where we can talk about infinite things, but in general, we're not going to be able to talk about infinite things on our computers because they're like actual finite devices in the world. So you really want to keep this sort of like mathematical, like platonic, like ideal world of infinities and sort of what we informally understand things to mean. Keep that on one side of your brain. You choose. And then on the other side of your brain, you're going to want to keep these like very concrete, very pragmatic representational choices that we're going to make in the computer. And you're going to want to hold them both at the same time while knowing that they're different. They're meant to overlap, but they're not the same. Okay, I have one more informal video coming for you about just the operations we're going to do on sets, and then we'll move into code. Thanks for sticking with me.